All right, welcome back. Here are the types of redox reactions. There's several different types. The first one is called a signal replacement or displacement. This is what we looked at the very beginning when we talked about redox reactions. All right, what they are is you basically have something in the elemental state, and then you have a salt of some sort. In this case, it's calcium sulfate. In the example I gave you was, I'm sorry, not calcium, copper sulfate. In the example I gave you earlier was copper nitrate. It doesn't really matter what ion you have. This is our spectator ion. That sulfate is a spectator ion. Notice the zinc is going from a 0 to a +2. How do I know that? Well, what charge does zinc always have? We talked about this. Zinc is one of those transition metals that only have one charge, and I told you to memorize. It's a +2. Remember, cadmium and silver were the other ones that you had to remember. Okay? And your copper is a +2. How do I know it's a +2? Well, do the crisscross applesauce. You also know that sulfate is a -2 charge from your polyatomic ion sheet. So because this is a 1-to-1 ratio, your copper has to be a +2 charge. So that's why they put a +2 here. Okay. So your zinc is going from 0 to +2. This is what's called a half reaction. Zinc to 2 plus. This is called a half reaction because it's only half of the reaction. So my zinc is losing electrons, so it's being oxidized. My copper, which is starting out as a 2 plus, is going to copper 0. That's gaining electrons, so that's being reduced. This is reduced, this is oxidized. But the signal replacement is basically where you have an element of some sort. Let's put element. And then you're adding it to some sort of salt. Remember, salt is where you have a metal and a non-metal. And your element is replacing one of these, either the metal or the non-metal, depending on what your element is. Okay, so like let me show you an example where you would be replacing your non-metal. So like let's say we have fluorine plus, let's say, sodium iodide. Okay, here's my elemental state, because that's 0. Here's my sodium iodide, let's call that a solid. This is a non-metal, so this is going to replace your non-metal. So you're going to form iodine in the elemental state plus NaF. Okay, that's a single replacement. Your fluorine is going from 0 to -1, so it's gaining electrons, so that's being reduced. Your iodine is going from a -1, iodine -1, to iodine 0. It's losing electrons, so this is being oxidized. Okay, so that's a single replacement. This is actually how a battery works. Batteries work by these type of redox reactions. They happen spontaneously. I don't know if you remember, but we did a lab where we took aluminum foil and we put it into a mixture of copper sulfate, I believe. Correct? Yeah, I think it was copper sulfate. It was like a blue solution. And what started happening is copper started coming out as like a reddish solid on the surface of the aluminum, and the aluminum was ionizing to become aluminum ions. Aluminum has a +3 charge. So this is the reaction that was happening. The aluminum foil was ionizing, so it was losing electrons, it was being oxidized, and your copper was being reduced, and these electrons were shuttling back and forth. Well, batteries work by basically what electricity is movement of electrons. So if you have electrons moving back and forth, you have electricity. So if you have a spontaneous reaction like this, and electrons are being produced, if you put a wire in there, you can capture those electrons, and you basically have a battery. All right, so this is how batteries work. You usually have a metal and then a solution. All right, like a cadmium battery. Everyone's heard of cadmium batteries. Lithium batteries. Lithium is one of your metals. Cadmium is one of your metals. I think they have. I think it's a cadmium nickel battery. I think is the common one, and I don't remember which one. I think the cadmium is your metal, and the nickel is the ion. And you do a redox reaction, you have a battery. Okay. And basically, how do you charge batteries? Well, you charge batteries by plugging them in. So what are you doing? You are pumping electrons into here to do the reverse reaction. You're pumping electrons in so that your copper metal starts gaining electrons. I'm sorry, starts losing electrons because the electrons are going to zinc. You're pumping electrons into zinc, which is causing it to actually become zinc metal. And the electrons are actually also are all coming out of copper to ionize again. All right, so that's basically what charging is. Charging is the reverse reaction Once you have it completely charged and everything now is in this state, you unplug it, and then the reaction proceeds all by itself spontaneously, and you have a battery. All right, this is quite a mess here. Let's erase that. So that's single displacement reaction. The next one is combination reaction, which is exactly how it sounds. You're combining two elements or two molecules together to form another molecule. So I have the element of nitrogen in the elemental state, the element of hydrogen in the elemental state, and I'm forming a molecule. All right, nitrogen goes from a 0 charge to a -3, so it's gaining electrons, that's being reduced. Your hydrogen is going from a 0 to a positive, it's losing electrons, so it's becoming oxidized, so it's being oxidized. Decomposition is the reverse. Basically, you have some sort of compound and you break it down into its elemental form. So it's the reverse of a combination reaction. All right. And then finally, the third type is called combustion. All right. Combustion reactions, basically, you are taking some sort of hydrocarbon. Okay, this is a hydrocarbon because it's composed of carbon and hydrogen, and you're adding it to oxygen, and your products are always CO2 plus water. Okay, your carbon is, now they show charges here, but this can get very, very confusing. This way works only for this example. Carbon can have a different oxidation state all depending on the molecule. So I don't want you to kind of know the numbers in the state. Just know anytime carbon gains oxygen, it is being oxidized. Very simple. And that's really the term oxidized that people kind of know. Oh, oxidized, you're gaining oxygen. I know it, but it also means loss of electrons. Okay, so anytime you see a hydrocarbon, a carbon and hydrogen, burn in oxygen, you always form CO2 and water. So that's just something you have to memorize. Also, if you have a hydrocarbon that has an oxygen attached to it, plus O2, you also get CO2 and water. And I'm going to show you one more example where you have a carbon, a hydrogen, and a sulfur. Oop. You can have the sulfur. I'm going to show you examples, or I'm going to talk about an example, a real life example that we deal with. You get CO2 plus water, but you also get SO2 in this case. Okay. These compounds, these organosulfur compounds, is actually something that we put in our natural gas. So natural gas has no odor. Ethane, butane, methane, those are what we call natural gas. They do not have an odor, okay? What the gas company does is they put a little bit of this compound in it, dimethyl sulfide. They also put other compounds. I don't know if they use this one particular anymore, but they have in the past. They put dimethyl sulfide, which if we put it in this kind of formula would be C2H6S. And when it comes into your house, into your pilot, and it burns either in your hot water heater, your furnace, or on your stove if you have a gas-powered stove, these compounds, these organosulfur compounds, have a horrible, horrible smell. Okay, they have like a rotten egg smell to it. Anyone that's ever smelled gas, which is pretty much everybody, you can smell gas, and it has that nasty smell, that rotten eggy smell, or that really pungent smell. Well, the gas company puts in a very, very less than 1% of this compound. Our noses are pretty sensitive to these sulfur compounds because they smell so bad. So the gas company actually puts a little bit of this into our natural gas so that when it goes into our house, and if there's a leak, we can smell it. Otherwise, there's no way that you would tell that you have a gas leak if they did not put something in there for you to tell. Okay. So because of that, so when it burns in your house, it burns in the CO2, H2O, and SO2. SO2 does not smell. It does not have a pungent smell. High concentrations of it will have a pretty bad smell to it. But mostly these organosulfur compounds really stink pretty bad. Okay, so that is combustion reaction. So I would like you to do this on your own. This is a very, very good practice to kind of figure out what type of reaction this is. You're going to have to be able to recognize these reactions. when you are taking the exam. You have to be able to look at it and tell, is it, first of all, is it a redox or is it a double replacement? All of these are redox, so you don't have to worry about that. But you'll get a practice problem sheet where you'll have a mixture of them. So you get practice on that. And then you have to tell me what kind of reaction. Is it a combination, a decomposition, a combustion, a single replacement, all those things. Okay? Um, the other thing I want to talk about, because I notice it on this sheet, so elemental states. Elemental state. Okay? We talked about, like if you have iron, that's in the elemental state. We also talked about the diatomic molecules. Have no fear of ice cold beer. Okay, so have no fear of ice cold beer. The other two I want to talk about is sulfur exists as S8 and phosphorus exists as P4. These are the elemental states for these. Okay, on the test, I am not going to have these for you, but you can see right here, you have a phosphorus. This is the only reason why I'm bringing it up, because you might see this in your problem sheets. And I don't want you to get confusing saying, well, you didn't talk about it. There's a lot of stuff I don't talk about that's actually in your book. I feel, it's not important to actually teach you every little thing where there's only one example of it. I only teach it to you if I see it. This, again, this isn't something you need to know for the exam. All right. So you can go through that. And when we come back, we will talk about gas-producing reactions.